We first show that subset sum is in NP. Given natural numbers w1, w2, w3 until wn, and a target w, the certificate that there is a solution would be the subsets wi1, wi2, wi3 until wik that is purported to add up to w, target w. In polynomial time, we can compute the sum of these numbers and verify that it is equal to w. We now reduce a non-NP complete problem to subset sum. Since we are seeking a subset that adds up to exactly a given quantity, as opposed to being bounded above or below by this quantity, we look for a combinatorial problem that is based on meeting an exact bound. The three-dimensional matching problem is a natural choice. We show that three-dimensional matching, which is polynomial time reducible to subset sum. The trick will be to encode the manipulation of sets via the addition of integers. So consider an instance of a three-dimensional matching specified by sets x, y, and z, each of size n, and a set of m triples, T, which is the subset equals to the product between x and y and z. A common way to represent sets is via bit vectors. Each entry in the vector corresponds to a different element, and it holds 1 if and only if the set contains that element. We adopt this type of approach for representing each triple T equals to xi, yj, zk in T. We construct the number wt with 3 n digits that has a 1 in positions I, n plus j, and 2n plus k, and a 0 in all other positions. In other words, for some base d which is greater than 1, wt is equals to d to the I minus 1 plus d to the n plus j minus 1 plus d to the 2n plus k minus 1. Note how taking the union of the triples almost corresponds to integer addition. Thus, ones filled in the places where there is an element in any of the sets. But we say almost because addition includes carries. Too many ones in the same column will roll over and produce a non-zero entry in the next column. This has no analog in the context of the union operation. In the present situation, we handle this problem by a simple trick. We have only m numbers in all, and each has digits equal to 0 or 1. So if we assume that our numbers are written in base d equals to n plus 1, then there will be no carries at all. Thus, we construct the following instance of subset sum. For each triple t equals to xi, yj, zk in T, we construct a number wt in base n plus 1 as defined above. We define w, the target w, to be the number in base n plus 1 with 3 n digits, each of which is equals to 1. That is, w is equals to the summations of n plus 1 to the ith power, where the summation is taken for I starting from 0 to 3n minus 1. We claim that the set T of triples contains a perfect three-dimensional matching if and only if there is a subset of the numbers, the set wt, that adds up to w. For suppose there is a perfect three-dimensional matching consisting of triples t1, t2, t3 until tn, then in the sum wt1 plus wt2 plus wt3 and so on plus wtn, there is a single one in each of the 3n digit positions, and so the result is equal to w, the target. So conversely, suppose there exists a set of numbers wt1, wt2, and so on to wtk that adds up to w, then since each wti has 3 ones in its representation, and there are no carries, we know that k is equals to n. It follows that for each of the 3 n-digit positions, exactly one of the wti has a 1 in that position. Thus, t1, t2, t3, until tk constitute a perfect